All right, everyone, welcome to your ultimate guide on isomerism. This is one of the most important concepts you'll hit in IGCSE organic chemistry. Honestly, if you can get this right, you are well on your way to acing those exams. So let's get right into it. I want you to imagine you've got a pile of Lego bricks, right? With that same set of pieces, you could build a super tall tower, or you could build a long, wide bridge. The pieces you used are exactly the same, but the final structures look totally different. Well, that right there is the core idea of an isomer. Okay, here is the official definition, and you absolutely need to know this one. Structural isomers have the same molecular formula. Think of that as your list of parts, the exact count of every single atom you have. But they have a different structural formula, and that's the blueprint. It's how all those atoms are actually connected together. Get that difference and you've got the foundation for everything else. So let's talk about our first type, chain isomerism. Just like the name says, this one is all about changing the main carbon skeleton. We're literally going to take the same atoms and just rebuild the main chain itself. Let's see that Lego analogy in action with butane. On the left, you see 4 carbons all lined up in a straight, continuous chain. Now, to make its isomer, we don't get rid of any atoms, we just rearrange them. We shorten that main chain to 3 carbons, and we take that 4th one and stick it on the middle carbon as a branch. And what we get is 2-methylpropane. See? Both are C4H10, but their structures are completely different. Now here's an exam tip, and this is a non-negotiable rule whenever you're drawing organic molecules. Carbon always, and I mean always, forms 4 bonds. As you're drawing your isomers, you have to constantly check this. If you draw a carbon with 3 bonds or 5 bonds, it's an instant mistake, and trust me, it's such an easy way to lose marks. Okay, next up is our second type, positional isomerism. Now with this one, the carbon skeleton actually stays the same. We're not rebuilding the chain at all. Instead, what we're doing is changing the location or the position of a key feature on that chain. We call that the functional group. Take a look at this example with alkenes. In but-1-ene, the double bond is sitting right there between the first and second carbons. To make but-2-ene, the 4-carbon chain stays identical, but we've just slid that double bond over to the middle. The backbone is the same, but the position of that functional group has changed. And it's the exact same principle with alcohols. Propan-1-ol has that hydroxyl, the OH group, on an end carbon. To create its isomer, propan-2-ol, we just move that OH group to the middle carbon. The 3-carbon chain itself is unchanged. Only the position of the functional group is different. Simple as that. All right, I need you to pay really close attention here. This next part is where so many students lose marks. Examiners absolutely love setting this trap, but after this, you are not going to be fooled. So here's the question for you. Take a good look at this molecule. Is this bent structure an isomer of a straight-chain butane? What do you think? The answer is no, absolutely not. This is the trap. Just drawing a straight chain and bending it around a corner does not make it a branch. It's the exact same molecule, just sort of twisted or bent on the page. It's still one continuous chain of 4 carbons. So how can you be 100% sure? You use what I call the pencil test, or the snake test. Imagine your pen is a little snake. Place it on the carbon at one end of the chain. Now, can you slither along that carbon backbone and touch every single carbon atom without lifting your pen? If the answer is yes, then it's a single continuous chain. It's just bent. It is not a branched isomer. Let's just put them side by side to make this crystal clear. On the left, you've got the bent chain trap. You can trace that whole thing in one go. On the right, that's a true branched isomer, 2-methylpropane. To trace that one, you'd have to trace the main chain and then lift your pen to get the branch. See the difference? They're not the same thing. All right, let's put this all together. Here is your final blueprint, your builder's code for tackling any isomer problem that comes your way on the exam. Here's your 5-step checklist. 1, nail the definition. Same parts, different build. 2, for chain isomers, you're rebuilding the skeleton. Shorten the chain and add a branch. 3, for positional isomers, you just move the special part, that functional group, to a new address on the same chain. 4, do not fall for the bent chain trap. Use that pencil test to be sure. And finally, number 5, your final check, always count your atoms and make sure every single carbon has 4 bonds. So there you go. You've got the blueprint. Master these rules, practice drawing the structures, and you'll be more than ready for any isomer question they throw at you in the exam. Good luck!